Hello friends. So today's lecture we will see what is stiffness method. In previous video we have seen what is stiffness method and we have seen what are the basic requirement and what does it mean, what is meaning of stiffness. So it is basically a displacement method where KDI, that is kinematic degree of indeterminacy, is very important to solve any structure. And there we have to find out the formation, we have to form K matrix, that is stiffness matrix, and then we have to apply your compatibility equation as theta is equals to K inverse into bracket P minus PL matrix. So where theta is your once again redundant matrix, that is displacement matrix, we will use joint displacement as a redundant over here because KDI is important and displacement method is there. And next one is a stiffness matrix. You have to find out this stiffness matrix which will be of square matrix depending on the number of redundant values. Next one is P matrix, which is called as a given action matrix or say given force or say moment matrix, which will be once again a column matrix. And next one is a PL matrix, that is once again it will be action matrix, either force or moment matrix, but it will be produced due to an external loading which is provided and over an entire structure. Okay, so let us see one example for this. Let us assume an example, that is ABC beam is given where 2-point load is acting on this particular beam. For AB span it is acting out at the center, that is at 2 meter from either of these joints, and then for BC span it is a point load is acting at 2 meter from B point. So we have to analyze this particular beam with the help of stiffness matrix method. So as far as stiffness matrix method is concerned, it is a displacement method. So in first step itself, there is very important that we have to find out kinematic degree of indeterminacy. Okay, for the beam we can easily find out kinematic degree of indeterminacy, where you can see two values are unknown joint displacement, that is theta B and theta C, which will be called as a slope or say rotation at joint B and joint C. Therefore we will use joint B as a node 1 and we will use joint C as a node 2. Okay, so let us theta B as a first redundant and theta C is a second redundant. Okay, and then in next step you have to find out stiffness matrix. Okay, so stiffness is nothing but, once again I want to tell you, stiffness is nothing but moment produced due to unit displacement at node. So here stiffness is nothing but moment or say action produced due to application of unit rotation at a particular node. So here if stiffness matrix is concerned, there we have decided two values is redundant, that is we have decided theta B and theta C as a redundant over here. So here stiffness matrix will be a square matrix of 2 by 2 order. So that stiffness matrix will contain 4 elements, likewise K11, K21, K12 and K22. Okay, how you will calculate this 4 elements? Let us see. So stiffness is nothing but the moment produced. Okay, but when it is produced, if we apply a unit rotation at a node. Okay, let us say we have seen that joint B is defined as a node 1 now, will be treated as a node 1, and joint C will be treated as a node 2. So first we will apply unit rotation at joint B, that is at node 1, that is theta B will be applying as a 1 value, that is unit rotation or say 1 radian value. Okay, see here if ABC is beam is, once again if you draw, and if B is rotating, okay, in figure you can see if B is rotating in a clockwise direction. Why it is a clockwise direction? Because we will treat clockwise as a positive value, so we will apply a positive unit rotation at each and every node. So here for node 1 we will apply a clockwise rotation at joint B. So if joint B is try to rotating, then in this particular figure you can see the behavior of your beam. B will try to rotate like this way, and if B is rotating, that means there has to be a moment produced at the joint B itself. So see here, for AB span, for just consider only AB span, for AB span, if B is rotating in a clockwise direction, therefore there has to be a moment which will be in a clockwise direction, which will produce that unit rotation, right? So this particular clockwise moment, how you will calculate, that is nothing but 4 ei theta by L, right? So in this, theta is nothing but your unit rotation, so I will write directly over here 4 ei by 4 only, okay, because theta is a unit value. So I will directly write down 4 ei by 4. 4 is the span of AB. Okay, so for span AB, the moment is produced is 4 ei by 4. And let us see what about the span BC. Once again, for span BC also, B is rotating. B is rotating in a clockwise direction. So therefore, there must be a clockwise moment as well for BC span, and that value will be equals to simply 4 ei by L only. Once again, theta is unit over here, so that value will be 4 ei by 3 only. That is 3 is the span of BC. Okay, so K11 is nothing but what? Once again, Kij, that is K11 elements of your stiffness matrix. So K11 is nothing but moment produced at node 1. First one value represents where moment is produced. Okay, first value will represent where moment is produced. That is moment produced at node 1. That's why K1. And next one is for what? So next one is due to unit rotation is applied at node 1 itself. Okay, so if we apply unit rotation at node 1, then what will be the moment produced at node 1? That value will be equals to simple K11. So if you see here, if joint B is try to rotating in a clockwise direction with unit rotation only, so there will be moment will be produced, two moment will be produced. For span AB it is 4 ei by 4, and for span BC it is 4 ei by 3. So if you add these two values, if you take algebraic sum of these two values, this will be your K11. So if you add these two values, it will be comes out to be 2.33 times of ei. That will be your K11 value. Okay, next we can say K21. Here you can see K21. Once again, it is called as a moment produced at node 2. Now it is moment produced at node 2 because first numericals, that is first two value, represents where moment is produced. So K21 is nothing but moment produced at node 2 due to application of unit rotation at node 1. Okay, so if I apply unit rotation at node 1 only, then what will be the moment produced at second node 2? That value will be equals to K21. So here once again you can see, if you try to rotate B joint in a clockwise direction with a say unit rotation, then let us forget about AB span because node 2 is at C point. So for C, if moment is produced at B is 4 ei by L with say positive value, that is in clockwise direction, so that value will be transferred to C value, but that transfer or say that particular carryover will be half of your moment produced at your node 1. So moment produced at node 1 is 4 ei by 3 for PC span I am talking about, and half of that value that will be carried over to next C value or say C joint. So that value will be equals to 2 ei by L. So that value 2 ei by L will be equals to K21. That is nothing but only once again moment produced at node 2 if you apply unit rotation at node 1. Okay, I guess you are getting. Okay, this is K11 and K21, and now K12 and K22 is remaining, but the K12 and K22, that means second value, that is 2 value, that is we have to apply unit rotation at node 2 now. That is we have to apply unit rotation at joint C. So if you see second figure, here you can see for second figure, C is now rotating in a clockwise direction only. So if you try to rotate C value, C joint in a clockwise direction, there has to be a moment which will be once again in a clockwise direction, and that value will be equal to simple 4 ei theta by L. Once again, theta is a unit, so it will be unit value. So this moment produced is 4 ei by 3, which is 3 is the span of your BC. Okay, so this particular moment will be a 4 ei by 3, and that value will be equal to simple k22, right? Because it is called as a moment produced at node 2 due to unit rotation is applied at node 2 only. Okay, clear? So moment is produced at second node only due to application of unit rotation at second node only. Okay, that is k22. That value will be 4 ei by 3. Now next is k12. K12 is what? Moment produced at node 1 due to unit rotation is applied at node 2. That means once again we have to see this particular figure only, and in this particular figure, if you try to rotate joint C by unit rotation, so the moment will be produced at joint C will be 4 ei by 3, and that particular half of this value will be carried over to your further end, far end, that is B point, and that value will be equals to 2 ei by 3. Okay, so in this regard you can denote as a near end and far end, where we are applying unit rotation. That particular end will be treated as a near end, and further end will be treated as a far end. So near end is very important, where moment is produced first and unit rotation is applied. Okay, and further end, in that further end we have to see how much value is carried over, moment is carried over. Okay, so here B is a further end, C is a near end. So at joint B, moment will be carried over. How much? What is the value of this moment? That is half of your 4 ei by 3, that is 2 ei by 3. Okay, that is nothing but your k1 to 2 ei by 3. That will become something 0.67 ei. Okay, so you from this you can easily find out this stiffness matrix. So k is nothing but ei is taken as a constant outside of your matrix. So it is 2.33 k11, 0.67, 0.67, which are called as a non-diagonal element, that is k12 and k21. That has to be exactly equal. Okay, and then k22 is 1.33. Now once again, if you try to apply compatibility equation in this particular solution, so we have to find out k inverse also. How to find out k inverse from k matrix? That is nothing but k inverse is nothing but 1 upon k determinant into adjoint of k matrix. So how to find out determinant now? K determinant, it is nothing but only the multiplication of your diagonal element, that is 2.33 into 1.33, minus multiplication of your non-diagonal element, so minus 0.67 square. So that value will be comes out with 2.65. Okay, so that will be your k determinant. And now how you will calculate adjoint matrix of k? So adjoint matrix, if k matrix is of 2 by 2 order, then it is very simpler to find out adjoint matrix. What you will do, you have to replace your diagonal element by each other, that is 2.33, that is k11, first element will be replaced by final element 1.33, and alternately, and so on, that is 1.33 also replaced by 2.33. And the next is non-diagonal element. We have to change the sign of your non-diagonal element, that is plus value will becomes now minus values. So here this will be your adjoint matrix. And now if if you want to find out k inverse, what you will do, 1.33, that is each and every element will be divided by k determinant. So 1.33 minus divided by 2.65 will be equals to 0.502. That will be your first element. Likewise, you will calculate all the 4 elements, that is element divided by k determinant. Okay, from this you can find out this k inverse. In next step you have to find out PL matrix. Okay, PL matrix. What is PL matrix? Once again, P denotes for your action, or say moment. Why I am talking about moment? Because I am trying because I am considering only theta as a here KDI value, that is joint displacement, as a redundant over here. So theta is redundant, that means action produced will be a moment, will not be a force, it will be a moment. So PEL matrix is nothing but moment matrix due to external loading. So for each and every joint we can easily find out the moment which will be produced due to external loading. So for this we have to find out fixed end moment for each and every span, for each and every joint. So we have seen what we can, how to find out fixed end moment. So here for span AB you can see for A joint, that is MFAB, will be equals to minus WL by 8. Okay, that is minus WL by 8. So you can easily find out minus 10 value, and for MFBA it will be plus value 10, that is plus value WL by 8, that is equals to 10 kilonewton meter. Next is for MFBC, it is not acting at the center, so this has to be equals to minus WAB square by L square. So that value will be comes out to be minus 6.67, and MFCB, it is plus value, that is in clockwise direction is will be the moment. So WA square B by L square is the value of plus 13.33 kilonewton meter. So PL matrix is nothing but once again moment produced at no, because it's a columnar matrix. So you will have only two elements as a column matrix. So how, which two elements? First we have decided two nodes only, B and C. So for B joint, what are the fixed end moments? That you have to check only the, you have to take algebraic sum of these two values. So that means MFBC plus MFBA has to be your first element of your column matrix, and next is MFCB is your second element. So MFBC is plus 10, MFBA is minus 6.67, will comes out to be 3.33, and next is MFCB is plus 13.33, will be as it is. Okay, this is your PL matrix, which will be moment matrix due to external loading. Next is P matrix, which will be 0, or say null matrix. Why is it so? Because there is no couple or any moment is acting on both the nodes. So we have decided two nodes B and C, or say 1 and 2. For both the nodes there is no acting couple on the node itself. Okay, there is no couple is acting on the node itself, so therefore this particular matrix will be a null matrix. Okay, and then we will use in next step, for step number 4, we will use compatibility equation, that is theta is equals to K inverse of P minus PL, where K inverse we have just calculated. Theta is nothing but your redundant values column matrix, theta B and theta C. Next is P matrix is a null matrix, and PL matrix we have just calculated as 3.33 and 13.33. So if you try to find out this theta B and theta C, how you will calculate? Once again, this EI will be say taken on left hand side, then you will find EI theta B as equals to 0.502, that is K matrix. That means you have to take multiplication of these two matrices. How you will get K11, that is 0.502 into your this PL matrix, that is 3.33, but it has to be taken as a minus, because here this will be minus sign will be there, P minus PL, therefore both the signs will be changed for PL matrices, PL matrix elements. So this will be minus 3.33 and minus 13.33. So EI theta B is nothing but 0.502 into minus 3.33 plus minus 0.253 into minus 13.33. So from this we will find out easily EI theta B. It will be comes out to be 1.7, and if you calculate EI theta C as minus 0.253 into minus 3.33 plus 0.879 into minus 13.33, it will become now minus 10.875. So this will be your EI theta C, EI theta B and EI theta C. Okay, and the next is so simpler. If you try to find out this AI theta B and AI theta C, next task is very simple. You have to find out final n moments, but for that you have to use your slope deflection equation. You have seen what is the slope deflection equation. So uh, we have found out these equations for each and every joints MAB. It is 2 AI theta B by L that is 4 minus MFAB. Okay, for MBA it is 4 EI theta B by 4 plus MFBA. Likewise, you can easily find out this SI equations and then try to replace the values of EI theta B and EI theta C in this equation, so that you will find final end moments. Likewise, you will find MAB will be comes out to be minus 9.115, MBA will be comes out to be 11.7, MBC will be comes out to be minus 11.66, and last one MCB will be equal to 0. So here you can see MBA plus MBC. If you try to find out these two values, that will be simply 0.04, which will be treated as a 0. That means this joint B will be in an equilibrium condition. Okay, so here this is your check. You can take the check for this from this one, that is MBA has to be equal to MBC, only the sign has to be changed. Okay, the next is how to draw SFD BMD. For that, first you have to find out free span moment. For both the spans you will find free span moment. For AB it will be WL by 4, for BC it is WAB by L. From this you will find both the values are 20 kN meter only, and both values are plus value, that is sagging bending moment only. Next you have to find out your other support reactions. How you will find other support reactions? Just take each and every span, consider each and every span separately, and use your equilibrium conditions for both the spans. Let us say for span AB, if you take summation of moment about point A, it will be equal to 0. You will find RBA, and then if you try to find out summation of FY is equals to 0, you will find RA. Likewise, we will find RC and RBC also, and from this we will draw SFD and BMD. Once again, SFD is very simple for this. Okay, and for bending moment diagram, you can see over here you have to draw first free span moment, which one has taken as a positive value, that is sagging bending moment, and next one is the remaining bending moment, that is hogging bending moment. Just we have calculated this as a final end moments in step number 5. That particular values has to be inculcated in bending moment diagram. So here for MAB it is coming out to be minus 9.15. So minus indicates hogging bending moment. Once again it is a minus. You have to superimpose plus values and minus values on each other. Therefore, we have drawn this minus value on positive side of your reference line. So here minus 9.15 and next is minus 11.7. So you have to just join these two values, these three ordinates. Say third ordinate is 0 at point C, so just join these three ordinates by simple straight lines. So this value will be some values are minus values, some values are positive values, and some are just cancelled with each other. Some area will be just cancelled with each other, that is both that area will be in both values, that is plus values as well as minus value. So here this is ends. So shear force diagram and bending moment diagram you can draw easily. Just only you have to find out this K matrix. How to find out K matrix? That is the only difficult part, you can say. From this you can easily find out, or easily you can solve any type of structure. You can analyze with the help of stiffness matrix method. Okay. Thank you. If you have any queries, you can contact me. Thank you so much.